You are a time traveler, right now. Sitting in that seat, you are moving through time. And I don't mean that in some cute greeting card way. We're all travelers on the river of time. No, I mean it in the hardest, most literal, most physically rigorous sense that modern science can offer. You are traveling through time at a rate that depends on how fast you are moving and how deep you are sitting in a gravitational field. And the rate at which your clock ticks. The clock in your chest, the clock in your cells, the clock in the atoms that make up every molecule of your body. That rate is not the same as the rate of the clock belonging to someone on the other side of this planet, or someone in orbit above us, or someone falling toward a black hole 10,000 light years from here. This is not a metaphor. This is measured. This is confirmed. This is as certain as anything we know about the physical universe. Time travel is real, but it is almost nothing like what you have been told. Now, I know what you're picturing. You're picturing a machine. A beautiful, ridiculous machine with dials and levers, or maybe a phone booth, or a DeLorean with flux capacitors. You're picturing someone stepping inside, punching in a date, 1776, or 2525, or the Cretaceous period, and vanishing in a flash of light to appear somewhere else in history. That image is so deeply embedded in our culture that it has become the definition of time travel for most people. And I want to be very clear about something. That image is not entirely wrong. Parts of it touch real physics. But the way most people understand it, the way it lives in our imagination, is about 90% fantasy and 10% a profound misunderstanding of what Einstein actually showed us more than a century ago. And the 10% that's real? That 10% is far stranger, far more beautiful, and far more unsettling than any science fiction movie has ever managed to be. Let me start where any honest discussion of time travel has to start. With a man who, in 1905, was a 26-year-old patent clerk in Bern, Switzerland, who could not get a teaching position, who was largely ignored by the academic establishment, and who in the span of a single year rewrote the foundations of physics so completely that we are still catching up to what he told us. Albert Einstein. And the thing Einstein told us that matters most for tonight is this. Time is not what you think it is. Time is not a river flowing at a constant rate from past to future. Time is not a backdrop against which events play out, ticking away uniformly for everyone, everywhere, at the same pace. That picture, Newton's picture, the common sense picture, the picture that feels so obviously right that questioning it seems almost insane. That picture is wrong. Not a little wrong. Fundamentally, structurally, deeply wrong. Einstein showed us. And every experiment we have conducted since has confirmed it, over and over, with increasing precision. That time is elastic. Time stretches. Time compresses. Time runs at different rates depending on your state of motion and the strength of the gravitational field you are sitting in. And this is not some tiny, negligible effect that only matters in exotic conditions. This is happening to you right now. Your head, right now, as you sit here, is aging slightly faster than your feet, because your head is farther from the center of the Earth, and therefore in a slightly weaker gravitational field, and therefore time runs a tiny, tiny bit faster up there than it does down at your ankles. The difference is absurdly small, billionths of a second over a lifetime. But it is real. It has been measured. We have clocks precise enough to detect it over a difference in height of about a foot. Think about that. The universe does not grant you a single, unified, universally agreed upon now. Your own body does not experience a single now. The top of your head and the soles of your feet live in slightly different time zones. And if that doesn't unsettle you at least a little, then I haven't explained it well enough yet. This is special relativity and general relativity working together, and they give us the two great engines of real-time travel. The first engine is velocity. Move fast, really fast, a significant fraction of the speed of light. And time slows down for you relative to someone who stayed behind. This is not an illusion. This is not some trick of perception. When you move at high velocity, the actual physical processes in your body, the ticking of every atomic clock, the firing of every neuron, the decay of every radioactive atom, all of it slows down as measured by someone watching you from a stationary frame. And from your perspective inside that moving frame, Everything feels perfectly normal. You don't feel sluggish. You don't feel time stretching. You look at your watch and it ticks away 1 second per second, just as it always has. But when you slow down and compare your watch with the watch of someone who stayed behind, yours has ticked off fewer seconds. You have aged less. You have, in every meaningful physical sense, traveled into the future. Not the distant future. Not yet. But the principle is the same, whether you're traveling at 1/10 of the speed of light or 99.9% of it. The faster you go, the further into the future you leap. And this is not theoretical speculation. We have tested this in 1971. And I remember when this happened, because it was one of those beautiful moments when physics moves from the blackboard into the real world. Joseph Haefel and Richard Keating put cesium atomic clocks on commercial airliners and flew them around the world, once eastward and once westward. When they brought the clocks back and compared them with identical clocks that had stayed on the ground at the United States Naval Observatory, the clocks disagreed. The flying clocks had ticked off a different number of nanoseconds than the ground clocks, and the disagreements matched precisely. What Einstein's equations predicted when you accounted for both the velocity of the planes and the change in gravitational potential at cruising altitude. Those pilots and passengers were time travelers. They traveled into the future by a few hundred nanoseconds. Not very dramatic, I grant you. Nobody is making a movie about gaining 200 nanoseconds. But the principle was confirmed. Time travel is real. It is physics, not fiction. And if the airplane experiment doesn't quite satisfy you, if nanoseconds feel too small to feel real, then let me give you nature's own demonstration, one that happens every second of every day in the atmosphere above your head. Cosmic rays. High-energy protons and nuclei streaming in from exploding stars and colliding galaxies. Slam into the upper atmosphere at nearly the speed of light and create a shower of particles, among them muons. A muon is a heavy cousin of the electron, and it is unstable. It decays. Its average lifetime, measured in a laboratory at rest, is about 2.2 microseconds. That is 2/millionths of a second. Even traveling at nearly the speed of light, a muon should only be able to cover about 600 meters before it decays. 600 meters. The upper atmosphere, where these muons are created, is roughly 15 kilometers above sea level. By rights, almost none of them should reach the ground. They should decay long before they get here. But they do reach the ground. We detect them. We detect enormous numbers of them. They are raining through your body right now, about 10,000 of them per square meter per minute. How? Because they are traveling so close to the speed of light that time dilation stretches their brief lives. From our perspective on the ground, their internal clocks are running slow. So slow that their 2 microsecond lifetime stretches into enough time to traverse the entire atmosphere. From the muon's perspective, it still lives only 2 microseconds. But the atmosphere is length contracted, compressed to a fraction of its rest frame thickness, so the muon has much less distance to cover. Either way you calculate it, time dilation or length contraction, depending on your reference frame. The answer comes out the same, and it matches what we observe. Nature does not merely permit time dilation. Nature depends on it. The world you live in, the particles that pass through your body, the radiation environment of the planet, all of it is shaped by the fact that time is not absolute. And then there is the Global Positioning System, GPS, which may be the most mundane and the most profound example of time travel in everyday life. The GPS satellites orbiting the Earth carry atomic clocks that are synchronized with clocks on the ground. But the satellites are moving at about 14,000 kilometers per hour, and they orbit at an altitude of about 20,000 kilometers, well above the surface, in a weaker gravitational field. Special relativity says their clocks should run slow by about 7 microseconds per day because of their velocity. General relativity says their clocks should run fast by about 45 microseconds per day because of the weaker gravity up there. The net effect: the satellite clocks gain about 38 microseconds per day relative to clocks on the ground. 38 microseconds. That sounds like nothing. But GPS works by timing signals to nanosecond precision. And if you did not correct for relativistic time dilation, the position errors would accumulate at a rate of about 10 kilometers per day. Within a week, your GPS would be useless. Within a month, it would be placing you in a different city. Every time you use your phone to navigate, every time a plane lands using GPS, every time a missile is guided to its target or a hiker finds a trailhead, every single one of those moments depends on the fact that Einstein was right about time. We are not speculating about time travel. We are engineering with it. We are correcting for it. We are building it into the infrastructure of civilization. Now here is where it gets genuinely strange, and I need you to stay with me, because this effect, this slowing of time at high velocity, is not linear. It does not scale in a simple, proportional way. It follows a curve, and the curve gets dramatically steeper as you approach the speed of light. At 10% of the speed of light, the time dilation effect is tiny, barely a fraction of a percent. At 50% of the speed of light, it starts to become noticeable. At 90%, it is significant. Time for you is running at about 44% the rate of a stationary observer. But at 99% of the speed of light, something remarkable happens. Time for you is running at about 1/7 the rate. And at 99.9%, 1/22nd. And at 99.999%, the ratio becomes so extreme that you could cross the entire Milky Way galaxy, 100,000 light years across, and age only a few years. Let me make that concrete. Imagine you get on a spacecraft tomorrow, and this spacecraft can sustain 1 g of acceleration. The same acceleration you feel right now from gravity, perfectly comfortable, no exotic technology required beyond an impossibly good engine. If you accelerate at 1 g for 1 year of your own experienced time, then decelerate at 1 g for 1 year, then turn around and do the same thing coming back. 4 years of your time in total. You would return to Earth having traveled far beyond the nearest stars. And Earth would have aged more than you. How much more depends on how far you went, and the answer is startling. A round trip to the center of the galaxy at constant 1 g acceleration would take about 40 years of your experienced time. But when you came home, 20,000 centuries would have passed on Earth. Everyone you knew would be dust. Their civilizations would be dust. The very continents might have shifted. You would have traveled 200,000 years into Earth's future, and you would have aged only 40 years. This is not speculation. This is the straightforward, uncontroversial prediction of special relativity, confirmed by every experiment we have ever devised to test it. Now, I can feel the question forming in your minds, because it is the same question everyone asks, and it is exactly the right question. That's traveling into the future. Can we travel into the past? And this is where the story becomes much harder, much more contested, much more strange, and I will be honest with you, much more uncertain, because the physics of traveling into the future is settled. It is done. We understand it. We have measured it. There is no controversy. But the physics of traveling into the past is one of the deepest unsolved problems in all of physics. And it touches questions about the nature of reality that we do not yet have the tools to answer. Let me tell you how I got tangled up in this question personally, because it is one of my favorite stories about how science actually works. Which is to say, messily, accidentally, and sometimes because a novelist asked a physicist the right question at the right time. In the early 1980s, I was writing a novel, Contact. Some of you may know it. Some of you may have seen the movie. Jodie Foster, very good, though they changed the ending and I wish they hadn't. The novel is about the first contact between humanity and an extraterrestrial civilization, and I needed my character, Ellie Arroway, to travel an enormous distance very quickly. At first, I used a black hole as a shortcut. It seemed plausible enough for fiction, but I wanted the science in my novel to be real science, or at least to not violate any known laws of physics in an embarrassing way. So I called my friend Kip Thorne. Kip Thorne is one of the great relativists of our time. He was at Caltech, and he knows general relativity the way a master carpenter knows wood. Not just the theory, but the grain and the stress points and the places where it bends and where it breaks. And Kip told me, very gently, that my black hole shortcut would not work. Anything that falls into a real black hole gets destroyed, torn apart by tidal forces, spaghettified, as the physicists like to say, crushed into the singularity. No passage through, no coming out the other side. Dead end. Literally. But then Kip said something that changed everything. He said, "What about a wormhole? And not just any wormhole, a traversable wormhole, a tunnel through space-time that you could actually pass through and survive." And he started thinking about it seriously, not as science fiction, but as a real question in general relativity. Could such a thing exist? What would it require? And out of that question, a question that started because a novelist needed a plot device, came one of the most remarkable papers in theoretical physics. Kip and his students, Michael Morris and Ulvi Yurtsever, published a paper in 1988 that showed traversable wormholes were solutions to Einstein's field equations. They were mathematically permitted by general relativity. And here is the part that made everyone sit up straight. A traversable wormhole, if you could build one and then manipulate it correctly, accelerating one mouth of the wormhole to near the speed of light while keeping the other mouth stationary, could, in principle, become a time machine. Not just a device for jumping across space, but a device for jumping backward in time. I want you to understand what happened there, because it is important for understanding how physics actually progresses. A question that began in fiction led to a result in real, rigorous, peer-reviewed physics. A novel inspired a theorem, and the theorem said, "The laws of physics as we understand them do not obviously forbid time travel into the past." General relativity permits closed time-like curves, trajectories through space-time that loop back on themselves, paths you could follow and end up at the same point in both space and time where you started. In other words, paths that take you into your own past. Kurt Gödel. Yes, the same Gödel, the logician who shattered the foundations of mathematics with his incompleteness theorems. Gödel found the first such solution in 1949. He showed that in a universe that was rotating, not our universe, as far as we can tell, but a mathematically valid universe, you could travel along a path that brings you back to your own past. Einstein was deeply troubled by this. He acknowledged that Gödel's solution was mathematically correct, but he suspected, he hoped, that the real universe had some mechanism to prevent it, some cosmic censorship, some law we hadn't yet discovered that would slam the door shut on backward time travel and keep causality safe. And this is where the story gets genuinely difficult, because as of today, as of right now, we do not know whether that door is shut. We do not know whether the universe forbids backward time travel or merely makes it fantastically difficult. Stephen Hawking. Stephen, who I loved arguing with, who was one of the most stubborn and brilliant people I have ever known. Stephen proposed what he called the chronology protection conjecture in 1992. And I want to be precise about what he actually said, because it is often misrepresented. Hawking did not prove that backward time travel is impossible. He conjectured that the laws of physics conspire to prevent it. He suggested that whenever you try to build a time machine, whenever you try to create a closed time-like curve, quantum effects would intervene. The vacuum fluctuations of quantum fields would build up to infinite energy at the chronological horizon, and the time machine would destroy itself before it could ever be used. He phrased it beautifully, as Stephen always did. It seems there is a chronology protection agency which prevents the appearance of closed time-like curves and so makes the universe safe for historians. Wonderful line. Characteristically witty. But notice the word he used, seems, not is, not I have proven seems. Because he could not prove it. The proof requires a complete theory of quantum gravity, a theory that unites general relativity with quantum mechanics. And we do not have that theory, not yet, perhaps not for a long time. So let me lay out for you, as honestly as I can, what we actually know and what we do not know about traveling backward in time. And I want to organize this not as a list of possibilities, but as a deepening of the problem. Because each layer you peel back reveals something stranger underneath. First layer, general relativity alone, in pure general relativity. Einstein's theory of gravity, treating space-time as a smooth, continuous fabric. Backward time travel is permitted. Closed time-like curves exist as valid solutions. Gödel's rotating universe. The Kerr solution for a rotating black hole, which has a ring singularity you could in principle pass through into a region of space-time containing closed time-like curves. The Tipler cylinder. Frank Tipler showed in 1974 that an infinitely long, extremely dense rotating cylinder would drag space-time around it so violently that closed time-like curves would form. The Morris-Thorne wormhole time machine I just described. All of these are valid solutions to Einstein's equations. General relativity does not forbid them. It permits them, almost casually, as if the universe doesn't particularly care about protecting cause and effect. Second layer, the energy problem. Every single one of these solutions, when you look at what they actually require to build, demands something exotic. The Tipler cylinder requires infinite length or matter denser than anything known to exist, the traversable wormhole. And this is the crucial point. Requires what physicists call exotic matter. Not exotic in the colloquial sense of unusual or expensive. Exotic in the technical sense, matter with negative energy density. Matter that gravitationally repels rather than attracts. Matter that violates what we call the energy conditions. The assumptions that general relativity normally makes about the kind of matter and energy that can exist in the universe. Now, does exotic matter exist? This is a fascinating question. Quantum mechanics says, maybe. The Casimir effect. The measurable attractive force between two uncharged conducting plates placed very close together in a vacuum arises because the vacuum energy between the plates is lower than the vacuum energy outside them. In a certain sense, the region between the plates has negative energy density relative to the surrounding vacuum. It is a tiny, fragile, laboratory-scale demonstration that negative energy is not strictly forbidden by the laws of physics. But the amount of negative energy produced by the Casimir effect is absurdly small. To hold open a wormhole large enough for a person to pass through, you would need negative energy on a scale that is. Well, let me put it this way. You would need to take all the energy the sun produces in its entire lifetime and somehow convert it into negative energy and focus it into a shell thinner than an atom. We are not remotely close to being able to do anything like that. Whether it is even possible in principle is an open question. Third layer, and this is where the real trouble lives, the paradoxes. If you can travel backward in time, then you can, at least in principle, change the past. And if you can change the past, well, then you arrive at the most famous headache in all of philosophy and physics, the grandfather paradox. You go back in time. You prevent your grandfather from meeting your grandmother. Your parent is never born. You are never born. But if you were never born, you never went back in time. So your grandfather does meet your grandmother. So you are born. So you do go back in time. And around it goes, a logical contradiction spinning in circles forever. Now, there are proposed solutions to the grandfather paradox, and some of them are quite clever. And I want you to hear the main ones because they reveal very different assumptions about what kind of universe we live in. The first solution is the Novikov self-consistency principle, proposed by Igor Novikov in the late 1980s. Novikov's idea is elegant and a little bit chilling. The laws of physics simply will not allow you to do anything in the past that creates a paradox. You can go back, you can walk around, you can observe. But every time you try to do something that would create a logical contradiction, shoot your grandfather, step on the butterfly, change the outcome of a battle, something will prevent you. The gun will jam. You will trip. You will have a change of heart. The universe conspires, through perfectly ordinary physical processes, to maintain consistency. There is only one timeline, and it is self-consistent, and your time travel was always part of it. I find this both beautiful and deeply unsettling, because it implies a kind of determinism that most people find very uncomfortable. The idea that even your free will, your choices, your intentions are constrained by the overall logical consistency of the timeline. The second solution is the many worlds interpretation. The idea, growing out of Hugh Everett's work in quantum mechanics, that when you travel back in time and change something, you don't actually change your own past. Instead, you create. Or perhaps more accurately, you enter. A branching timeline, an alternative history, a parallel universe in which events unfold differently. Your grandfather still met your grandmother in the timeline you came from. That timeline still exists. You haven't created a paradox. You've just moved to a different branch of a vast, ever-splitting tree of possibilities. David Deutsch at Oxford has done serious work on this, showing that quantum mechanics and time travel can be made consistent if you accept the many worlds framework. And I will tell you honestly, I do not know which of these solutions, if either, is correct. I do not know if any human alive today knows. This question sits right at the intersection of general relativity, quantum mechanics, and the philosophy of identity and causality. And at that intersection, we have more questions than answers, more fog than clarity, more honest confusion than confident knowledge. But I want to take you somewhere even deeper now, because there is an aspect of time travel that most popular discussions completely ignore, and it may be the most important aspect of all. And that is the question of what time actually is. We talk about traveling through time as if time were a place, as if the past is a location you could visit, like Paris or the Cretaceous, if you could just find the right vehicle. But is that true? Is the past still there? Does it exist in any meaningful sense? Is the year 1776 sitting somewhere in the structure of the universe, waiting to be visited? Or is the past gone? Really, truly gone. Not stored, not preserved, not accessible. Just gone? Because these are genuinely different physical pictures, and they lead to genuinely different answers about whether backward time travel is even coherent as a concept. In the picture that relativity gives us, the block universe, as philosophers call it, the answer is startling. The past is still there. The future is already there. All of space-time. Every moment, every event, every configuration of every particle from the Big Bang to whatever end the universe comes to. All of it exists as a single, four-dimensional structure. Past, present, and future are not fundamentally different. They are just different locations in this structure. The way north and south are different locations on a map, but neither is more real than the other. Your sense that the present moment is special, that now is uniquely real, that the past has faded away and the future hasn't happened yet. That sense, in the block universe picture, is an illusion. A powerful, persistent, emotionally compelling illusion, but an illusion nonetheless. Einstein himself believed this. When his lifelong friend Michele Besso died in 1955, Einstein wrote to Besso's family, "Now he has departed from this strange world a little ahead of me." That signifies nothing. For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion. Einstein died a few weeks later, and I have always found those words both comforting and terrifying. Comforting because they suggest that the people we have lost are not gone, not really, that they still exist in the fabric of space-time as surely as a city you have left behind still exists even after you've driven away from it. And terrifying because they suggest that the flow of time, the very thing that seems most fundamental to our experience, is not a feature of reality, but a feature of our limited perspective on reality. Now, if the block universe is the correct picture, if all moments exist equally, then backward time travel is at least conceptually coherent. You are not traveling to a place that doesn't exist. You are traveling to a different location in a structure that is, in its entirety, real. But if the block universe is not the correct picture, if the past genuinely ceases to exist once it has passed, if the future is genuinely open and undetermined, then backward time travel is not just difficult, it is incoherent. There is nowhere to go. And I will confess to you, I do not know which picture is correct. I have thought about this for decades. I have argued about it with physicists and philosophers and anyone who would sit still long enough. And I find myself drawn, almost against my will, because the implications are so strange. I find myself drawn to the block universe. Not because it is comfortable. It is profoundly uncomfortable. But because it is what the mathematics of relativity seems to be telling us. And I have learned over a long career that when the mathematics tells you something strange, you should pay attention, even when, especially when, it contradicts your intuitions. But here is where it gets truly interesting, and where the story of time travel connects to something much larger, something that touches the deepest questions in physics today, because quantum mechanics tells a different story about time than relativity does. In quantum mechanics, the future is genuinely open. The outcome of a quantum measurement is not determined until the measurement is made. The universe, at the quantum level, seems to be making choices, rolling dice, as Einstein famously complained. in real time. The present moment, in quantum mechanics, is special. It is the moment of actualization, the moment when possibilities become facts. And this is not just a philosophical difference, it is a mathematical difference. The equations of quantum mechanics treat time differently than the equations of general relativity. In relativity, time is a coordinate, a dimension, like space, that you can move through in either direction. In quantum mechanics, time is a parameter, a background clock that ticks forward and only forward, marking the evolution of quantum states from possibility to actuality. These two descriptions of time are inconsistent. They cannot both be completely right. And reconciling them, building a theory that incorporates both the elastic, democratic, bidirectional time of relativity and the flowing, asymmetric, forward-only time of quantum mechanics. This is the central unsolved problem in theoretical physics. It has been the central unsolved problem for nearly a century. It goes by the name quantum gravity, and it is the reason we cannot answer the question of backward time travel definitively, because the answer depends on the nature of time itself, and we do not yet understand the nature of time itself. I want to tell you something about the arrow of time, because it is the piece of this puzzle that I think is most neglected and most important. We all know that time has a direction. The past is different from the future. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. People age and die, but don't unage and undie. There is an arrow, a clear, unmistakable, experientially undeniable arrow, pointing from past to future. And this arrow is deeply mysterious, because the fundamental laws of physics, the equations that govern every particle and every force, are almost entirely time-symmetric. Run them forward, run them backward. Both solutions are equally valid. The laws of physics, at their deepest level, do not prefer a direction. They do not care whether time runs from past to future or from future to past. Both are permitted. Both are equally physical. So where does the arrow come from? The standard answer, and it is a good answer as far as it goes, is entropy. The second law of thermodynamics. Disorder increases. Systems evolve from ordered states to disordered states, from unlikely configurations to likely ones, from low entropy to high entropy. And this gives us an arrow. The future is the direction of increasing entropy. But this just pushes the question back one step. Why was entropy low in the past? Why did the universe begin? At the Big Bang, 14 billion years ago, in a state of extraordinarily, absurdly, almost incomprehensibly low entropy. The initial conditions of the universe were fantastically special, fantastically ordered, fantastically unlikely. Roger Penrose has calculated that the probability of the universe starting in a state with entropy as low as what we observe is something like 1 part in 10 to the power of 10 to the power of 123. That is not a large number. That is an incomprehensibly, inconceivably small probability. And yet it happened, and the arrow of time. Our entire experience of past and future, of cause and effect, of memory and anticipation, of birth and death, all of it flows from that one initial condition. Now, what does this have to do with time travel? Everything, because the arrow of time is what makes backward time travel paradoxical in the first place. If time had no arrow, if past and future were truly symmetric, then traveling backward in time would be no more problematic than walking north instead of south. The paradoxes arise because the arrow of time creates an asymmetry, causes precede effects. Memories record the past, but not the future. You can influence what comes after you, but not what came before you. Backward time travel would reverse that arrow, at least locally. And it is the collision between that local reversal and the global arrow that creates the logical knots. The grandfather paradoxes, the bootstrap paradoxes, the information paradoxes, that make backward time travel so philosophically explosive. So when people ask me, and they ask me all the time, at every public lecture, at every dinner party, every time someone finds out I've thought about this, Carl, will we ever have a time machine? Here is what I tell them. I tell them what I've told you. You already have a time machine. It's called velocity. It's called gravity. You are using it right now. Every airplane flight, every GPS satellite, every particle accelerator, every cosmic ray slamming into the upper atmosphere. All of these are time machines, real time machines, doing real-time travel, confirmed by real experiments. The future is accessible. We know how to get there faster than the normal rate. The engineering is beyond us today for anything dramatic. We cannot yet build a spacecraft that travels at 90% of the speed of light, but the physics is settled. The physics is done. Forward time travel is real. But the past? The past is another matter entirely. The past may be forever out of reach. Not because we are not clever enough, but because the universe itself may be constructed in a way that forbids it. Hawking may be right that there is a cosmic censorship, a chronology protection agency built into the fabric of reality. Or Hawking may be wrong, and the universe may permit closed time-like curves under conditions we haven't yet imagined. I cannot tell you the answer. Nobody can. Not because we are lazy or stupid, but because the answer requires a theory of quantum gravity. A complete, self-consistent theory that unifies the two great pillars of modern physics. And we do not have one. We may be close. String theory, loop quantum gravity, causal set theory, a dozen other approaches. Brilliant people are working on this, and have been for decades. But close in fundamental physics can mean another year or another century, and anyone who tells you they know when we will solve this problem is guessing. Here is what I want to leave you with. Not an answer. Because an honest scientist does not hand you certainty where none exists, but a way of thinking about the question that I believe does justice to how strange it really is. We live in a universe where time is not what it seems. It bends, it stretches, it runs at different rates in different places. It may not even flow. It may be a frozen, four-dimensional landscape that our consciousness traverses like a traveler walking through a country that already exists in its entirety. The past may still be there. The future may already be there. And the distinction between them, the arrow, the direction, the sense of becoming, may be the deepest and least understood feature of physical reality. We know. Not suspect, not believe, but know, with the full weight of experimental confirmation, that traveling into the future is possible, and that we do it every day, and that with sufficient technology we could do it dramatically, leaping centuries or millennia in a single human lifetime. That part is settled. We do not know whether traveling into the past is possible. We do not know whether the universe permits it or forbids it. We do not know whether the paradoxes that seem to arise are genuine contradictions or merely failures of imagination. Problems that will dissolve when we understand the deeper theory. And I am not embarrassed by this uncertainty. I am thrilled by it. Because uncertainty of this kind, uncertainty at the frontier, uncertainty about the deepest features of reality. This is not a failure of science. This is science at its most alive. This is the universe telling us that it still has secrets, that the story is not finished, that the most fundamental questions about the nature of time and causality and reality remain open. Every civilization, every culture, every child who has ever imagined going back and undoing a mistake or going forward to see what happens next. Every one of them was asking a question about the structure of the universe. And what we have learned in the last century is that the universe takes the question seriously. Time is not rigid. Time is not absolute. Time is part of the fabric of reality, woven together with space, curved by matter and energy, flexible in ways that Newton never imagined and that even Einstein found disturbing. Whether that flexibility extends far enough to allow us to revisit our own past, that is a question for the next generation of physicists, the next revolution in our understanding, the next great leap in the long, improbable, endlessly astonishing human project of figuring out what kind of universe we actually live in. And if that question doesn't keep you up tonight, at least a little, then I haven't done my job.